Welcome back for another exciting episode of Calculus 1. Today, limit laws. I've got this beautiful table right here. We'll have even more of it. It looks pretty daunting at first. I think it's my job to show that it's really not that daunting, that our limit laws are here to make your life easier, not harder. They are surprisingly nice, and also they are a testament to all the work that's gone into thinking about limits and that they work well. So in any field, as you start to develop new machinery around it, you're going to want to try to create an algebra of that field. And so limit laws are really telling us, hey, what happens when we add or subtract limits or multiply or divide them? In other words, how do we do algebra with limits so that we don't have to do those tables of numbers? No one wants to do those tables of numbers if we can avoid it. And these amazing limit laws are going to help you skip all those tables of numbers and come up with even nicer formulas and nicer rules that might even skip limits altogether. But as a little bit of motivation, just think for a second about something like learning how to square things. When you learn how to square, hey, if I have numbers like 2 plus 3 and I square them, okay, this is most definitely not equal to 2 squared plus 3 squared. Okay, we have to actually FOIL those out, right? Or in this case, it's going to be 5 squared. If I had the natural log of 2 plus 3, this is definitely not going to be equal to natural log of 2 plus natural log of 3. Oops. This is the property that you're trying to use there is something called linearity, that you can distribute across plus signs, which you can't for squaring or natural logs or sines or tangents, but we have different rules, right? We've got different rules for squaring called FOILing. We actually don't really have a very good rule for natural logs, but we do have rules for trigonometric functions. If you remember all of our angle sum formulas and things like that, that's the algebra of trigonometry. Luckily for us, the algebra for limits is really nice. It's really linear is what's happening here, but it's even more so than that. So I am going to say probably don't bother writing this giant table. We're going to try to learn this thing by example, but it would be nice if you tried to read it at some point to work on your ability to read things that look scary. It's a really good skill in math. Basically what this table is saying is, hey, suppose you know one of your limits. Suppose you know the limit is x goes to a of some function f. And you also know a limit, also when x goes to a, same a, but of a different function g. Well, then what can you say about the limit of f plus g? And this is telling you, actually, you can do them separately. We can split up across that plus sign, which is exactly what we couldn't do with squaring or a natural log or sines or cosines or most of the other functions in the world. And same with subtraction, and same with multiplying by constants, and same with multiplying each other, and same with dividing. They're just the nicest things in the world, right? So this is going to let us do a lot of simplification and get to a lot of answers by just doing really basic algebra. And sometimes this section almost seems boring because the rules are so nice. So they're so nice that I don't even need you to remember them like by name. I just need you to be able to use them when the opportunity arises. So you don't need to memorize 1, 2, 3, 4, 5 or anything like that. In fact, those numbers change depending on who you ask. Okay, we're going to have these 5 basic ones, and they will also, from those 5, once you believe those, then you get a few more, right? Once you have multiplication, then you get exponents and roots and things like this. And so we'll talk about these couple of extra ones as well that are going to help us take limits very, very fast for most of our favorite functions. Okay, so what we're going to do is, rather than read off all of these laws kind of one at a time in the formality, I think they're better just demonstrated with an example because they are exactly what you want them to be. Here's some familiar functions. This f, x squared minus 1 over x minus 1. On several occasions now, we have found the limit of that as x goes to 1. This was actually our example from the very first section, so you should be able to find that either by table or by simplifying this thing by now. We have all agreed that this is a 2. this one, 3x, well, you could do a table, or you could graph it. 3x is just a line that behaves quite well, and what you get out is just what you get when you plug in a 1 here. So it's just going to be a 3. Okay, so what the first limit law says is, hey, if I have the limit as x goes to 1 of the sum of these functions, we'll do this one nice and slow, this is equal to the limit of them separately. So I am allowed to evaluate these on their own first. Now, lucky for us, we know what those are. We know that those up here, we pre-computed them, this is a 2, this is a 3, and that is a 5. Okay. What you will often see is just a little arrow game, like, hey, I know what this is. This whole thing is going to a 2. This whole thing is going to a 3. And we can take these shortcuts because of the limit laws. However, if you are rewriting these, I do expect to see limits in each case, because I don't want this equal sign to ever be connecting to things that aren't literally and absolutely equal. So do be careful about including these limits. Those limits go away once I evaluate them, right? Once I say, oh, the limit of this whole thing is 3, and so that limit can go away. So this is a 5. Great. Easy peasy. Number 2 is the same thing, except for that it is with a minus sign. So x squared minus 1 over x minus 1 minus 3x equals, well, I know what this is, and I know what this is. This should be 2. Oops, I lost my blue theme. Let's go back. Here we go again. All right, I really care. Oh, man. I need to edit this like crazy. X squared minus 1 over x minus 1 minus 3x. So if there is a minus sign, well, the same good stuff happens. We can do them separately. So this just becomes 2, because we already know what that limit is on its own, minus 3, we know what that limit is on its own, equals -1. Okay? So because of these limit laws, and because I know these parts individually, this goes very, very fast. It also lets me just split up and worry about the harder one and leave kind of the easy one separately if I didn't know them ahead of time. Okay, limit law number 3, we're going to cruise through these. Let's go ahead and pick a number here. Let's say that this is a 5 times x squared minus 1 over x minus 1. So what this literally says is that I can pull that 5 out and let it multiply the whole limit. But what it in practice says is, well, this is just 5 times that limit I already know, right? 5 times 2. So multiplying by a constant, it just multiplies by a constant. How nice is that? Moving right along, what if I multiply my two functions together? What would that look like? Well, I'm going to even switch the order here. 3x times x squared minus 1 over x minus 1. And what this limit law tells me is that if these on their own have limits, this is going to 3, this is going to 2, then the whole thing had better go to 3 times 2 is equal to 6. Ah, so nice. So nice. Forgive me, I am going fast because there's a lot to get through. You can always replay or slow down the video if you need to. So far what do we have? That if we add two functions on the inside, we can evaluate their limits separately. If we subtract, we can evaluate their limits separately. If we multiply by a constant, we just take the limit and multiply by that constant. If we multiply two functions, we can do it separately and multiply on the outside. That's pretty amazing. What's left? Probably division. So let's go ahead and see what happens if we divide these. There's already some division in there. Gotta be a little careful how I write this. Big parentheses. Parentheses are your friend. Use lots of them. Especially with compound fractions like this. This is telling us we can do these two separately, so this should be just 2 over 3. Perfect. because the top goes to 2 and the bottom goes to 3. Everything we ever wanted. However, there is a catch. If you look up here at this limit law, it says this only works if your denominator is not going to 0. We still need to be really, really careful about going to 0. It's not really clear what number would come out if I was dividing by 0. I wouldn't really have a number to write because that is not defined. So this limit could exist for the bottom, but if it's going to 0, it just means I have to do a lot more work. So, for instance, in this case right here, x is going to 0, not 1. And notice that our denominator, if we tried to plug in a 0, we would get a 0 in this big fraction over here. So we're kind of in trouble. If in any case you're dividing by 0, you got to do more work. All right, our limit laws are not going to save us. That more work, luckily for us, usually just means simplifying. Most of the time, it's just simplifying. So let's just do that real quick here. Let's just see what's going on. If I just divide this fraction, here I'll go ahead and write this first one as a fraction. Notice when I divide by a fraction, it means I multiply by the reciprocal. Okay. When I write it like that, it becomes a little bit more clear that this x crosses out with this x. And I get something that looks like, forgive me for writing across the page here, the limit as x goes to 0 of 3x minus 1 over 1. If I plug in a 0 there, I just get -3. Very nice. By the way, me just plugging in a 0 there, how did I know I could do that? My limit laws actually tell me, and they will more so in a bit, exactly that I am allowed to plug into this thing. So speaking of which, what are these more complicated ones? I'm going to whiz through these as well. 6, 7, 8, 9, 10, 11. They're not really more complicated. They are just a few other functions that follow from the first 5. So what number 6 says is, hey, here's a function I know, that's our old f. I'm going to take it to 5, and so this says I am allowed to say the limit of this inner thing is a 2. That's a constant up top, so I can just write this as 2 to the 5. My computer science students should know what 2 to the 5 is. You gotta know all your powers of 2. It's 32. 7 is great. It says, hey, I'm gonna take a limit of a constant. That constant doesn't care what x does. X can go to 1, it can go to 7, it can go to 19. The number 5 is still going to be a number 5, no matter what x does. So this is just a 5. So constants are just themselves. X's are going to go to whatever x is going to. Great. In this case, it's a 1. That's the property I used up above to just plug in. In this case, this is redundant with the one before, but hey, if I have a power of x to a constant, well, then I can just plug that in as well. 5 to the 3rd is 125, I hope. Same with cubes, squares, other roots. I'm allowed to just plug them in so long as they are, I'm going to a positive number for even roots. I don't want to accidentally take a square root of a negative number. So this one really is just the cube root of 5. Man, that's nice. And 11 is really the same thing. 10 is just using an x, 11 is using an entire function. And so in this case, this is just the cube root of 2, which I cannot simplify. Quick reminder, cube root of 2 is 2 to the 1/3. So really this is also telling us that fractional exponents are just fine as well. Neat. So, in summary, you can add, subtract, multiply, and divide separately in limits, so long as you don't divide by 0. If you have to divide by 0, you probably got to do some more work. Constants stay as they are. X's go to whatever number x is going to. Powers of x's you can plug in, and roots of x's you can plug in. These together give us huge classes of functions where we can just plug in, right? That's what's happening here is this one is just plugging in, or for a power of x, we're just plugging in to get that number out. And so in the next video, we'll talk about entire classes of functions where we're allowed to just plug in.